Hello, in this lesson we are going to look at the uncertainty in measurement. The essential idea here is no measurement can be exact. For a measurement to be exact, we need a measuring instrument with marks infinitely close together, which is clearly impossible. So if you have a thermometer, something like this, okay, so there are some marks on the thermometer. Here is, for example, the 0 point. And now we have marks on the thermometer, and we can make even some other marks in between these marks. For example, this is 1, this is 2, and we can make some other marks in between 1 and 2, but again they are not infinitely close to each other. So in this case, this measuring device cannot be exact. Let's look at the resolution of the measuring instruments. The resolution is the smallest amount, it is the smallest absolute amount of change that can be detected by a measuring instrument. For example, this meter stick, this ruler, can measure up to 1 millimeter. We can measure in millimeters. That's why the resolution for this meter stick is 1 millimeter. On the other hand, for example, resolution of this thermometer is 0.1. It measures every increase or decrease in the temperature, every increase of 0.1 temperature change. Similarly, here we have a voltmeter. So what is the resolution of this voltmeter? It's going to be, this is 0, this is 5. So 1, 2, 3, 4, 5. And as you see, we also have some marks in between 0 and 1, between 1 and 2. So this device can measure voltages of 0.5. So the resolution of this device is going to be 0.5. This is 0.5 resolution, this has 0.1 resolution, and this has 1 millimeter resolution. Let's look at the zero error. Reading with no zero error. For example, reading a thermometer. What do we mean reading with no zero error? If this is your device, here is the zero of your device, and this is the zero, the point where you are going to measure the distance or something else. If these two zeros are aligned exactly, it means you are going to read with no zero error. For example, if we are going to read this thermometer, here is the zero, this is the zero temperature, and this zero temperature is specified by the manufacturer of the thermometer. They have calibrated it to 0. We don't need to while measuring the temperature, we are not aligning our thermometer with the 0. It is already done for us. We are just making the reading. Let's look at the measuring with zero error. For example, reading with a meter ruler. I will explain it, but first of all, here, if you are going to, this is the point that you have to start measuring. But if you put your measuring instrument somewhere here, they are not exactly aligned. So there is a measuring with zero error. So for example, if you are going to measure with this meter stick or ruler, and if you start measuring from this corner, you are going to make some measurement error because the zero starts at this point, okay, and you are going to align your, assume you are going to measure this distance, okay. First you need to align this 0 with the beginning of this length, and aligning them by hand is not exact. We are going to make some mistakes, we are going to do some error here. That's why in aligning our instrument with the object that we are going to measure, it is not always perfect. That's why we have, in this case, we have some measuring with zero error. But for example, measuring with the thermometer, we don't have an zero error because the 0 is already specified for us by the manufacturer. Let's look at the error and uncertainty. Error is the difference between the actual value and the calculated value of any physical quantity. I'll give you an explanation for this one. Also, uncertainty means the range of possible values within which the true value of the measurement lies. What do I mean? Assume the true value of the speed of light is here at this point, and you measured something bigger than the true value. This is the measured value. And if you do another measurement, maybe you can get some value here or some value here or somewhere here. Every time, in every measurement, it includes some error. You are going to measure different values, but this is the true value. So the error, the absolute error is the difference between the true and measured value. On the other hand, because of the measuring devices, we also have some uncertainty. What do I mean? Assume, for example, you want to measure this length with a meter stick again. Okay. Now we are going to put marks on our meter stick. Okay, these are centimeters. 1, 2, 3, 4 centimeters. Assume this is also divided into millimeters. We have marks here. 2, 4, 6, 8, 10. So now in measuring this length, it is exactly 1, 2, 3. Okay, 3.2, but not 3.4. This is the point 3.2, and this is the point 3.4. So our measurement is going to something between 3.2 and 3.4. So we have some uncertainty here. That's why all measurements include some uncertainties. That's why when you are measuring something, you have your measured value. You are going to include the uncertainty, amount of uncertainty. Here it's going to be 1 millimeter. And you are going to subtract the amount of uncertainty. So your true value is going to be between this and this point. So let's look at the amount of uncertainty. When you are reading, no zero error. If your device is just help you to read, you don't have zero error. You don't need to line up your instrument with the beginning. For example, in reading the thermometer, in reading a balance, in reading a measuring cylinder, you don't need to align the 0 point. That's why in reading an instrument, for example, these instruments, there is no zero error here. That's why the uncertainty, amount of uncertainty during reading, only if you have a device, you are going to read it, the amount of uncertainty is going to be 1/2 resolution. But if you are going to do some measurement, for example, for the ruler, you have to line up with the 0. While you are lining up with the 0, you are going to make some mistakes, and also while reading it, you are going to make some mistakes. In this case, the total amount of uncertainty will be equal to the resolution of the instrument. For example, measuring with the ruler, with a stopwatch or protractor, we are going to both read and also measure. That's why the amount of the resolution, amount of uncertainty will be equal to the resolution. Let's look at the precision and accuracy. Accuracy is the measurements are close to the true value. As much as your measurements are close to the true value, that much it is accurate. But precision is measurements are close to each other. When your measurements are close to each other, it means you have some precision. So here is the accurate value, for example. If this is the accurate value at the center, and these are your measurements. In this case, they are very far away from each other and they are not at the center. It means that there is low accuracy and low precision. But let's look at this one, for example. These are close to the center. Okay, so there is a little bit accuracy here. Here we have accuracy, but we have low precision. These marks are close to the center, but they are away from each other. There is low precision. So let's look at this one. These dots are very close to each other. It means there is high precision and low accuracy because they are away from the center. If they are at the center and they are close to each other, then your measurement will be both accurate and precise. Let's look at random and systematic errors. What is a random error? It refers to the random fluctuations in the measured data, and these fluctuations in the measured data they are due to the readability of the instrument, the effects of something changing in the surrounding between the measurements, and the observer being less than perfect. And there are some other reasons also which causes to the random measurement. For example, if you are using a poor technique, you are not care about the parallax, for example. In this case, you are going to make random errors. For example, if you are going to look at this level of the water, and if you look at this from this perspective, you are going to measure this value. If you look at from this perspective, you are going to measure this value, and if you look at from here, then you are going to measure something different. So each time you are different from different perspectives, and you are going to measure different amounts. So this is a cause of the random error. So random error can be reduced by averaging. If you take the average of these values, you can get you are going to make little absolute error. You are going to be close to the actual value. On the other hand, the systematic error is due to the instrument being out of adjustment. If your instrument is not very well adjusted, then we are going to make some systematic errors. For example, a meter stick might be rounded at one end. So if it is rounded, for example, at one end, okay, if this is your meter stick, and if this end is a little bit rounded, and for example, the 0 point is starting here, but you measure from this point, it means every time you are going to add this much of error to your measurement. An instrument that is improperly calibrated, as I explained, they should be calibrated. For example, thermometer should be calibrated to the 0 point. When the temperature is equal to 0, it must exactly show the 0. But if it is not very well calibrated, it's going to make every time it's going to make the same amount of error. For example, again, for poor technique also can cause some systematic error, but in this case, you are always looking from the same perspective. For example, here, you are always looking with this angle, theta, okay? And this is not correct. You must look at from here, okay? Even though you are always looking from the same perspective, it is not correct. You are going to add some systematic error. So the amount of systematic error is almost same in every measurement. So systematic errors are usually difficult to detect. One way, for example, detecting the systematic error, for example, you are going to measure you are going to look at you are making a graph of temperature with the pressure, for example, and you did your measurements, for example, you get such a value, okay? In this case, this graph is going to show that when the temperature is 0, pressure is also 0. But this is not correct. When the temperature is 0, there is still some pressure. If you have such a graph, it means most probably you have done some systematic error. While we never know the true value exactly, we attempt to find its best estimate. So our measurement is going to be equal to the best estimate, also plus minus absolute uncertainty. You are going to make some reading, some measurement, okay? For example, you read 2.5, and then there are some uncertainty in your measurement. You have to include the uncertainty, for example. It is something like this. So when expressing your measurement results, this is going to be your best estimate, and this is going to be your uncertainty. We are in science, we represent our calculation results like this. So the best estimate of your measurement is at this point, okay? But since it includes some uncertainty, okay, the true value is between this level and between this level. The true value is somewhere here, and this is your measurement, and it includes some uncertainty. So we are going to express our measurement something like this. For example, this one, it will be 2.5 plus minus 0.2. In this case, this distance will be 0.2, and here also will be 0.2. Okay, for example, the length of a rod is measured using part of a meter ruler that is graduated in millimeters as shown below. Here it is. Now we are going to measure this length. In measuring this length, what will be our result? So here, first of all, we are going to make an aligning of this the object to our 0 point, but here we are going to align it to 3. It's not important. Then we are going to make our measurements 1 centimeter, 2 centimeters, 3, 4, 5 centimeters. So we are measuring 5 centimeters here. And also there is some uncertainty here since this meter ruler measures up to 1 millimeter. So the amount of the uncertainty is equal to the resolution. Why? Because both we are reading here, we are reading at this point, and we are aligning at this point. So the uncertainty is going to be equal to the resolution. So the amount of the length is 5 centimeters, and plus minus 1 millimeter. Okay. So we are going to express our results 5 centimeters plus 1 millimeter, and since both should be the same unit, 1 millimeter is equal to 0.1 centimeter. This is going to be the correct answer. When you are doing several measurements, when you are making repeated measurements, what will be your uncertainty? The measurement in this case is going to be equal to average plus minus absolute uncertainty. How we are going to measure the absolute uncertainty during repeated measurements? We are first going to find the average value, and it's going to be sum of all measurements divided by number of measurements. First we are going to find our average. Then the absolute uncertainty is going to be equal to the range divided by 2. Within your measurements, we are going to determine the maximum value and the minimum value, subtract them and divide by 2. It will give you the absolute uncertainty. Then you are going to write your mean here, mean here plus minus the uncertainty, absolute uncertainty. Then how we are going to calculate the fractional uncertainty? It is equal to delta x over x, amount of uncertainty divided by the measured value. And the percentage uncertainty is equal to delta x over x times 100. We will do the examples of these calculations. Let's look at, for example, this one. Assume you are measuring the angles with protractor. These are your measurements. Okay. So how should we express the angle of refraction? As I said, this is a repeated measurement. First, we need to find the mean. If we measure the mean, it's going to be equal to, if we calculate the mean, it will be 45.4 degrees. And the range of these measurement values will be equal to the highest value minus the smallest value, which is 47 minus 44. So this is going to be equal to 3. Then how we are going to determine the uncertainty? Let me denote uncertainty with U. It is range divided by 2. So this is going to be equal to 1.5. Now how we are going to express our measurement? Our measurement will be, so the average plus minus the uncertainty. Here is the average, this is the mean. Now as you see here, our values, our individual measurements are two significant figures. I'm also going to round these to two significant figures. It will be 45 plus minus, and here is the uncertainty. It is going to be rounded to only one significant figure. So if I round this one, it will be 2. So our measurement will be 45 plus minus 2. Let's look at another example. Here we have some resistances and they are measured. Okay, what should the student report as the resistance of the lamp? These are the different measurement values. How we are going to report our measurement result? First, again, let's look at the mean. If we calculate the mean here, it is going to be equal to 643 ohms, and range here will be equal to the maximum value is 666 minus 609. Okay, so this will give us 20 plus minus I'm sorry, this is going to give us 57 ohms. Now let's look at the uncertainty. Will be equal to range over 2. It will be 57 divided by 2, and it is going to be equal to, uncertainty will be equal to 29. Okay, so the measurement value is going to be equal to, we should report our measurement as the mean is 643 plus minus the uncertainty is 29. Okay, so let's calculate the fractional uncertainty. I'm going to write it fractional uncertainty, FU. Remember, the fractional uncertainty was delta x over x, so it will be equal to 29 divided by 643, and the fractional uncertainty will be equal to 0.05 if we round it. What about the percentage uncertainty? I'm going to write PU. It is delta x divided by x times 100. Just I'm going to multiply this value, and I'm going to multiply this value with 100. 0.05 times 100, it will be 5%. Okay, let's look at this example. A student measures the voltage shown. Here is the voltage is 1.999. What are the absolute, fractional, and percentage uncertainties of this measuring device? Okay, so the resolution here is equal to 0.001. This digital voltmeter can measure every change of the voltmeter. Every 0.01 volt will be determined by this voltmeter. That's why the resolution is equal to 0.001. The absolute uncertainty, on the other hand, is going to be 1 over 2 resolution. Why? Because we are just going to read it. We don't need to align to the 0. The calibration is always done. That's why we are going to only read the resolution. I mean, absolute uncertainty will be equal to 1 over resolution. It will be 0.005. Then fractional uncertainty is the uncertainty divided by the measured value. And if we divide these two values, we are going to get 0.0003. And percentage uncertainty, this fractional uncertainty times 100, and this is the amount of percentage of the uncertainty, 0.03. So Let's look at this example. If this is not example actually, if data are to be added or subtracted at the absolute uncertainty, if you are going to find the amount of uncertainty in adding two measurements, then you are going to add the uncertainty of the first measurement plus the uncertainty of the second measurement. For example, we have measured a distance of 3.4 with this uncertainty, and we have another length measurement 2.2 plus minus 0.1, and we want to measure these two values. I mean, we need a plus b. So how can we calculate a plus b? First, we are going to these are the best estimates, and if we sum them up, they are going to be 5.6, and then we are going to sum the amount of the uncertainties. As you see here, we have given the formula. When you are going to sum two values, the uncertainty in the summation will be equal to the uncertainty of each measurement. And similarly, if we are going to find a minus b, then we are going to subtract these two values. And we are going to subtract these two values. If we subtract them, it's going to be equal to what? It will be going to be equal to 4.4 plus minus, and the amount of the uncertainty again is going to be the sum of two uncertainties. It's going to be 0.3. So even though we are subtracting the best estimates, these are the best estimates, and these are the these are the best estimates, and these are the best estimates, and these are the uncertainties. So in this case, even though we are making subtraction in our calculation, again we are going to sum the uncertainties up and write our results like this. What about if we are multiplying or dividing the numbers? In this case, how we are going to calculate the percentages? Uncertainties, how to calculate the fractional or percentage uncertainties. For example, if y is equal to a times b over c, then this measurement, we are going to measure a, we are going to measure b, we are going to measure c, and all of these measurements are going to include some uncertainties, and we are interested in the uncertainty in the y. This is going to be our value, and since each variable has some uncertainties, what is the total uncertainty in our measurement? And the formula for this case is going to be equal to delta y over y equals delta a over a plus delta b over b plus delta c over c. For example, if you multiply with d, then you are going to add delta d over d. Or even though if you are not multiplying with d but dividing by d, again you are going to add. If it is no matter it is multiplication or division, always you are going to add them up. Let's look at an example. For example, this is a and this is b. These are two measurements. We have their uncertainties, and we are interested in a times b. Now, a includes some uncertainties, b includes some uncertainties, and if we multiply them, we are going to get capital letter A. For example, we are measuring the area. So what is the uncertainty in the area? This is our formula as I explained here. Delta A over A is going to be delta A over A plus delta B over B. And also assume we are interested in A over B, for example. In this case, again, even though this is division, we are going to calculate the uncertainty in B. Delta B over B is equal to delta A over A plus delta B over B. As you see, this one and this one are completely the same. In the case of multiplication and division, we are going to sum them up. So let's do our calculations. For A times B and B for A over B. And here is A times B. If I just multiply 3.4 with 2.2, I'm going to get this value. What about A over B? If I divide 3.4 to 2.2, this is going to be our value. And what is the delta A over A, the fractional uncertainty? Delta A over A, 0.2 divided by 3.4 will give us this value. And for the B, that 0.1 divided by 2.2 is going to give us this value. So now we can calculate the uncertainty in area. We are going to calculate delta A. So here delta A is going to be equal to, if we rearrange this formula, delta A will be equal to A times delta A over A plus delta B over B. Okay, so here we have multiplied with the A, which is this one. Okay, this is equal to A, and multiplied with the delta A over A plus delta B over B. They are here. So it's going to give us this value. This is the uncertainty in the area. And we are going to express our result area. It's going to be equal to, here our values are two significant figures. So I'm going to round this area. Area is equal to 7.48. If we round it, it is going to be 7.5 plus minus. Similarly, here we have two significant figures for the uncertainty, and the amount of uncertainty in area was 0.778. If we round it, it's going to be 0.8. And similar calculation is done for the division here. This is the A over B. This is delta A over A. This is delta B over B. And this is our amount of uncertainty in the B. And if we are going to express it again, I'm going to round this value. It's going to be equal to 1.5. I'm also going to round this value. It's going to be 0.4, 0.2. Let's look at this example. And a cylinder has a radius of 1.60 plus minus 0.1 centimeter and height of 11.5 plus minus 0.1 centimeter. Find the volume. So what is the volume formula for the volume of the cylinder? V is equal to pi. Volume is equal to pi r square h. Okay, so it is going to be equal to pi times r is 1.60 square times h is 11.5, and after this multiplication we are going to get 92.488 centimeter cube, and I'm going to round it, and I have to round it to three significant figures. This is going to be rounded to look at this value. This is going to be 0.5, 92.5, 923. I'm sorry, 900. I'm going to. Sorry. Let me round it to. Let me do the rounding from the beginning. So this multiplication is going to give us 92.488, and I have to round it to two significant figures, and this is going to be equal to 92. And now let's look at the uncertainty in volume. Delta V over V is going to be equal to delta R over R. It's equal to pi r squared divided by 2, and plus delta R over R. Why? Because we have 2 R times R, plus delta H over H. So in this case, this is going to be equal to 2 times, we have 2 of delta R over R, 2 times delta R is given 0.01 divided by R is 1.60, and plus delta H over H. Delta H is equal to 0.1 divided by H 11.15. So in doing this calculation, we are going to get what? In doing this calculation, delta V over, and the volume is equal to 92, okay, equals, and summing these two values are going to give us 0.0. It's going to be equal to 0.02120, and I mean this value is equal to this value. And if I multiply with 92, then delta V, amount of uncertainty, delta V will be equal to, if I multiply 92 with this one, it is going to be equal to 1.96075. And then how we are going to express our measurement, our volume will be equal to 92 is the best estimate plus minus the amount of the uncertainty. I have to round this one. This is 1.96075, and it is going to be rounded to 2. That's why plus minus 2. And uncertainty as error bars in graphs. When representing data as a graph, we represent uncertainty in data points by adding error bars. The length of the error bars at each point represents the uncertainty range of that point. So for example, let's look at an example. We are measuring two meshes, M1 and M2, and we have measured the M1 as 1.49, and this is the uncertainty. Here is the second measurement. This is the uncertainty in the second measurement. So let's look at the let's specify. Let's show this measurement with error bars. This is the best estimate, 1.56, and plus minus 0.6. So if we add 0.06 and subtract 0.06, then we are going to have error bars. Similarly, for the first measurement, here this is going to be 1.49. This is the best estimate, and we are going to add our uncertainty. It is going to be 1.49 minus 0.03, this level, and this is going to be 1.49 plus 0.03. So in representing our data points, we are going to show our error bars. Let's show an example here. in measuring, for example, the masses, for example, in grams. These are your measurements. For example, this is the first measurement, this is another measurement, and these are some other measurements, and this is the line of best fit. This is the representation without the error bars. But if you include the error bar to each of these measurements, you have to include it something like this. And it's shown here. Every measurement with their error bars are indicated here, and this line is passing so that it passes through all of the error bars. It does not skip any of the error bars. For example, here this is not shown very well. At least this one should be something like this, so that this line is passing through this one also. So measurements that have uncertainties in both variables can be shown by drawing error bars, horizontal and vertical, for each variable. For example, if you have two variables here, these error bars are showing the horizontal uncertainties, this shows the vertical uncertainties. Let's do an example and finish here. And the vertical uncertainty here will be, this is 0.5, this is 0.7, so it is going to be 0.2. The horizontal uncertainty, on the other hand, this is 0.6, this is 0.7, this amount is equal to 0.1. Okay, that's it. Thank you for listening. See you next time.